Flywheel. A flywheel used in machines serves as a reservoir which stores energy and releases it during the period when the requirement of energy is more than the supply, and stores energy during the period when supply of energy is more than the requirement. A flywheel does not maintain a constant speed, it simply reduces the fluctuation of speed. It does not control the speed variation caused by varying loads. Turning moment diagram for a four-stroke engine. A turning moment diagram for a four-stroke cycle internal combustion engine is illustrated below. In a four-stroke internal combustion engine, there is one working stroke after the crank has turned throughout two revolutions, that is 720 degree or 4 pi radian. Here means uh, neg- suction stroke. The pressure inside the engine cylinder is less than the atmospheric pressure during the suction stroke. Therefore, a small negative loop is formed. Compression stroke. During the stroke, work is done on the gases by the pistons, resulting in a higher negative loop. Expansion of working stroke. The fuel's bonds and the gases expands rapidly, producing large positive loop in this stroke. Useful work is done by the gases. Exhaust stroke. Work is done by the pistons to clear out the gases, forming another negative loop. Work done per cycles. The work done per cycle can be calculated using the formula work done per cycle T mean by into theta, where T mean torque, theta angle turn in one cycle, theta is 22 pi for two stroke engine, 4 pi for four stroke engine. Fluctuation of speed. The difference between the maximum and minimum speed during a cycle is defined as the maximum fluctuation of speed. The ratio of maximum fluctuation of speed to the mean speed is termed as coefficient of fluctuation of speed, Ch n max by n mean minus n mean by n mean coefficient of steadiness. The reciprocal of the coefficient of fluctuation of speed is known as the coefficient of steadiness denoted by m. M is equal to 1 by Cs n mean n max minus n mean. Maximum fluctuation of energy. The turning moment diagram for a multi-cylinder engine is represented below. The horizontal line AG represents the mean torque line. Let A1, A3, A5 be the area above the mean torque line, and A2, A4, A6 be the area below the mean torque line. Energy deficits. Let the total energy in the flywheel at point A is equal to E. The maximum fluctuation of energy daily is given by daily E max minus E mean half I omega max square minus omega mean square daily I omega mean square CS, where I mass moment of inertia of the flywheel about its axis of rotations, omega max maximum angular speed during the cycle, omega mean minimum angular speed during the cycle, omega mean omega max plus omega mean by 2. Coefficient of fluctuation of energy CC, maximum fluctuation of energy by work done per cycle. Dimensions of the flywheel rim. Cross section and tensile stress analysis of flywheel rim. Let D mean diameter of the rim in meters, R mean radius of the rim in meters, A cross sectional area of the rim in meter square, rho density of the rim material in kg per meter cube, and speed of the flywheel in RPM. Omega angular velocity of the flywheel in radian per second, B linear velocity as the mean radius in meter per second, omega into R sigma tensile stress or hoof stress in Newton per meter square due to centrifugal force. Total vertical upward force tending to brush the rim across the diameter xy is given by F is equal to 2 rho A R square omega square. This vertical upward force induces a tensile stress whose stress resisted by 2P, where 2P is equal to sigma A, equating the bursting force to the resisting force to rho A R square omega square to sigma A. Sigma rho R square omega square is equal to rho V square. Hence, the linear velocity can be expressed as V is equal to root over sigma by rho. Mass of the rim m volume into density by d. A rho from this required cross sectional area is derived as a m by pi d rho.